In thermal property testing, a single good-looking result does not equal reliable data. Confidence in thermal conductivity, diffusivity, or heat capacity measurements comes from repeatable outcomes under controlled conditions. If results can't be reproduced within reasonable uncertainty limits, the data becomes difficult to trust, defend, or apply in real-world conditions. Inconsistent measurements don't just create technical uncertainty, they undermine confidence. Engineers may question material models, production teams may struggle with process control, and customers may lose trust in reported performance. And while repeatability alone doesn't guarantee accuracy, as you can have it consistently wrong data without repeatability, accuracy can't be meaningfully accessed at all. Reliable thermal data begins with consistency. When results vary unexpectedly, the root cause is rarely the instrument alone. Most variability comes from small, compounding inconsistencies in how tests are performed. Sensor contact. Variations in pressure and surface flatness significantly affect heat flow. If one test is performed with a 1 kilogram weight and another without, the difference in pressure changes sensor contact and therefore the result. Sample preparation and placement. Differences in thickness, alignment, or surface condition introduce variability. If samples aren't flat and smooth, the measurement reflects contact resistance, not just material properties. Environmental conditions. Ambient temperature shifts, airflow, vibration, and humidity can influence measurements, especially for low conductivity or porous materials. User technique. Inconsistent setup procedures between operators can introduce systematic differences that appear as random noise. Even when using the same instrument and method, uncontrolled variables can shift results enough to mask true material behavior. Understanding where variability originates is the first step towards controlling it. Improving repeatability isn't about running more tests, it's about tightening control over how each test is performed. Standardized setup procedures. Create clear, step-by-step protocols. Ensure even pressure and proper sensor placement every time. Consistency in execution matters more than the number of repeats. Control sample conditions. Maintain consistent surface preparation. Samples should always be flat and smooth to minimize variability from contact resistance. Stabilize environmental conditions. Minimize airflow, temperature drift, and vibration. Allow samples and sensors to reach thermal equilibrium before testing. Avoid placing systems near AC vents or windows. Lock in test parameters. Keep heating power, test duration, temperature range, and data processing methods consistent. Detailed testing notes ensure future users replicate the same conditions. Train operators consistently. Small differences in technique can lead to systematic variation. Training, checklists, and documentation reduce operator-induced variability. When procedures are standardized, variation becomes meaningful rather than just being measurement noise. Repeatability problems rarely occur suddenly. They usually show up as subtle warning signs, like results drifting over time without setup changes, good repeatability within one operator but poor between operators, increasing spread after method adjustments, frequent need to rerun tests to get expected values, data clusters shifting depending on who performed the test. These patterns often indicate uncontrolled variables, not real material changes. Catching these warning signs early prevents wasted testing time, incorrect conclusions, and costly downstream design or manufacturing errors. Repeatable thermal data doesn't come from running the same test over and over until the numbers look right. It comes from controlling test conditions, sample preparation, environment, and technique, so that each test is fundamentally comparable to the last. When variability is understood and managed, repeatability improves naturally. Trends become meaningful, comparisons become defensible, and thermal data becomes genuinely useful for modeling, design decisions, and quality control. Reliable results aren't about chasing numbers, They're about building a process that produces trustworthy data every time.